So after we looked at that equation, we then jumped ahead a bit, and because I thought it's a bit easier to explain shear flow in terms of a single channel section rather than an I section. So the argument was that if you've got a section and if that section is thin, why worry about stresses? Let's just worry about shear flow. So there's not much difference between the shear flow equation and the stress equation. Okay. So with a single channel section, there's a position known as a centroid, which is there. I was going to point there. So that's the centroid of the section. And the centroid of the section, as you can see, is within the section itself. So it's along that line there, but the centroid is within the section. For similar sections, which are monosymmetric, there's another position known as the shear center. Now, when we talked about doubly symmetric sections, like back-to-back sections there, the centroid and the shear center are the same position. Okay. But when we've got a section, and that section is monosymmetric, there's another position called the shear center, which is not the same in this case as the centroid. And the thing that's magical about the shear center is that if you can pass your shear force down through that through the shear center, then your section will not twist. And why should you worry about twisting, particularly when you've got an open section? If that section is allowed to twist, you will find that it reaches its failure load very easily, because an open section doesn't really have much strength and torsion. So with open sections, it's very important to detail the load path such that the load path passes through this shear center. And if the load path passes through the shear center, then the section is not likely to twist, and you're more likely to be able to extract more load from the section. So when we've got the shear center, we can follow what's known as the shear flow down the section. So we've already said that most of the shear is taken by the web. So this vertical member down here, that's taking most of the shear force. But there will also be the complementary horizontal shear force, or the shear flow going in from that flange and going in from that flange. So simplistically, if you can turn that shear flow and that shear flow into a force, you will find that the section would want to rotate because those two are couples. And if you can pass that force down through the shear center, then you will find that that and that also form a couple, and so the section doesn't want to twist. Okay. Everyone understand, or have I confused everyone? Sure.
I don't understand how you're wanting to pass the force through the shear center if that's not actually on the section. Like it's got that eccentricity away from it.
Yeah, you'll have to design a bracket.
Oh.
Yeah. Okay.
So.
Good question. I'll remember that for next year. So I
you weren't using the
yeah.
You were using
Yeah. No, good question. Okay, thanks for that. So yeah, you would have a bracket, or you would bolt something to it, and you would go to all of this trouble just to avoid the shear force, or just to make sure that the shear force passes through the shear center. Okay. Yeah.
How do you know which way an arrow is going?
Yeah, very good question. That's why I drew that up there. So you make your cut, and then one way one arrow goes, one way the other one, the arrow goes the other way, so it really doesn't matter which way it goes. But we're thinking in terms of flow, so an easy way to think of it is, we know the vertical shear force is going from that to there, and we just flow round. Okay, so that's why there's an analogy with flow. So imagine if you had some water up here, the water would flow through the flange, down the web, and then back out here. So imagine if that's a pipe, hence the word flow. So that's just a way that might help you think about how the shear flows through the section.
So if we were looking at the other side,
Yeah, if you looked at that side of the cut, maybe it's going round that way, and if you looked at that side of the cut, maybe it's going round that way, but you would have exactly the same problem, and the shear center would end up at the same position. Okay, any more questions? Okay, all right. So everyone is quite okay with the idea that there's a centroid of a section. Is everyone okay with there being a centroid? And everyone's okay with this idea that there's another position, which is important when it comes to a cross section, where if you can pass the load through there, then the shear through there would form a couple with that one, and that would counterbalance this horizontal shear force or shear flow going through the flanges. Okay. Yep.
How does it form a couple? Both of them are going in the same direction.
Yeah, that's sort of puzzling me a bit. Let's just say that we can take, because that's the way it's explained to me, so I was scratching my head the other day, but you can, it's not really clear which way the shear forces flow, but we know that that's coming down there, and if I say take that point and take a moment about that point, everyone describes it as a couple, but I was really puzzling about that. So that that force going through there is likely to want to rotate in that way, and then these two are likely to want to rotate in the other way. Okay. All right. Okay. Yeah.
How's the magnitude of the couple?
Well, you will have to do an integration to work out, to convert this QF into a force. So you will integrate QF from here to here, work out the force. That would be identical to the integration from here to here. So you end up with one force there and one force there, which is going to cause a twist. And then if you assume a lot of the shear comes down through here, and then that needs to be equal to, that times that distance has to be equal to these two multiplied by that distance. Confused, or how am I doing? All right, so we've got one force going there and one force going there, and that's going to want to twist the section like that. Is everyone okay with that? Okay. And then let's say we've got that point there, a distance E away, and we've got the shear coming down from there. That's wants to twist in that way. So one twist is clockwise, the other twist is counterclockwise. If you can make those two equal by adjusting this shear center, they're going to cancel each other out. Yeah.
If the distances between like the shear center and those forces are different, the side forces are different from the distance between the middle force and
Yeah.
the shear center, are they going to have to be different magnitudes?
Well, the distance from there to there is not the same as the distance from there to there. So we've got a force there which is not equal to that force there, and then we've got another force there which is not equal to that force, but that force is equal to that force, which causes a rotation. Let's just stop the word couple. And we've got a position here, and we've got the shear force coming down there, and that's going to want to give another rotation, and the two have to balance each other out. So, all right. Any more questions? Yeah.
When you say rotation, is it rotation about centroid?
It doesn't matter where the rotation is, because the moment is defined as force times distance, and in this case here, if you took moments about that point, you've got that force times that distance, subtract that force times that distance. That's why it's called a couple. So the definition of the couple is force, assuming that force and that force are the same. So that force and that force are the same, so the couple is that force multiplied by the distance between the two forces. Okay, any more questions? Have you all done couples before? Okay, all right.